So in the last video, we saw this Peter-Weyl theorem. So after we show the density, we can now decompose the L2 as a bunch of these E pi, where each E pi are kind of spanned by these matrix coefficients. And because of that, it allows us to do some kind of Fourier analysis similar to what we did in the abelian case. All right, so the first thing we can do is that if you consider the L2 space. So let's do some L2 theory. That looks like the Planck-Charron theorem we had. So if you have an F inside the L2 of G, and if you look at what happens to the L2 space, well, we know the L2 space can be decomposed as a bunch of these E pi, where you basically take one from each equivalence class. And we know that for each E pi, we have this, if I fix orthonormal basis, so let's say fix orthonormal basis, let's say E pi 1 up to E pi of D pi for the each of these E pi, these spanned by these matrix coefficients, then we can define the pi ij as basically the matrix units. You take the inner product, apply it on ej, and then you inner product with ei. So we proved before that in square root of d pi of these pi ij, and that's going to be an orthonormal basis for the each of these e pi. So basically, I have that all of these d pi, square root of d pi, pi ij, here pi is some irreducible representation, equivalence class of that, and I take all of these, that's going to be an orthonormal basis for the L2 space. Okay, so you have a nice description of the L2 space. And the nice thing about the L2 is that once you have an orthonormal basis, you can now have a decomposition. So your function f, you can think about it as a function you inner product with your orthonormal basis, d square root d pi, pi ij, you take their inner product, and then you multiply by the same thing, you multiply by the d pi, pi ij, all right? So let's just write this out a little bit. So you can move the d pi to the front. So this is the summation. I should say this is really the summation over pi first, and then for each pi you sum over all the ij between 1 and d pi, okay? So you take equivalence class pi, and you move the d pi outside, and you say, well, let's take the summation of the ij going from 1 to d pi. And then this integral is essentially just the f of x, pi ij of x, the conjugate. You're taking the L2 inner product, and then you have the dx, okay? And then you multiply this whole thing by pi ij, okay? If you let's say cij of pi, that's just going to be equals to d pi times this integral, let's say fx conjugate pi ij of x dx, then what you end up with is a kind of an L2 expansion of your f. So your f is now become the summation over all the irreducible unitary class, and then you sum over all the ij going from 1 to d pi of these cij pi times a matrix, a basic matrix coefficient. Okay, so you write it this way. Okay, so basically the you can use the these pi ij, you know, they're both orthogonal to each other. Their inner product is going to be equals to 1 over d pi if they're the same and 0 otherwise. And then from there, you can get the L2 norm of f is essentially just a bunch of these Cij. So if you do the 2 norm squared, that's essentially just equals to the summation over all the pi. And then you do the each of these Cij squared. Okay, so ij to d pi, and then you have the Cij, the whole thing square, and then you need to multiply the pi ij inner product with itself, which give you 1 over d pi. Okay, so that's what you have. All right, so that looks very nice. All right, so if you so before we move on to the next topic, I just want to let you observe that this is just a generalization of what we have in the abelian case. So if your G is abelian, and let's say assume G is also compact, and then what you have is that this G hat is going to be discrete, because the dual group of a compact group is always discrete. So what you have is that from the Planck-Charles theorem for the abelian analysis, so the F is going to be just equals to the summation of these integral f of x pi bar of x holding bar dx, and then you multiply by the corresponding character. Okay, so here I write the summation because this is the G hat has the discrete topology. So this is just equals to the Fourier transform. Okay, so this is the f hat of pi. Okay, so this is essentially just the Fourier inversion formula, but now we basically replace each of these f hat by these Cij. Okay, you integrate again these matrix unit instead. Okay. So that looks nice, all right. But there is one problem with this kind of approach, is that as you can see that your pi ij really depends on your choice of the orthonormal basis. Okay, so for each different orthonormal basis you choose for your representation, you may end up with different pi ij, and that's just difficult to consider. So most of the time, we want to do something that's independent on the choice of your orthonormal basis for these E pi, or basically for your the finite dimensional representation. So let's try to do the following. So let's do the following definition. So I want to define, let's say for f inside the L1 of G, let's define the Fourier transform. You essentially do the really similar stuff, okay, except now that you have the pi is no longer a character, so the f hat of a pi, this pi is no longer a character, it's just a unitary representation. So you do the pi x, the whole thing star dx, okay. So this pi x is just, you understood it as you can either think about it as a d by d matrix, okay, or you think about it as an operator acting on the h pi. So this integral is defined using these inner products. For each inner product, you have a scalar value integral, and then you put them together to get a matrix value integral. But you can also just think about it as an integral of a bunch of operators. Here, your f is in L1, so this is certainly integrable. So this is going to be inside the matrix of d pi by d pi matrix. Okay. So if you consider the ijth entry of this this Fourier transform I've had, the ijth entry is just no other than you integrate the ijth entry of this pi x star, but pi x star being the conjugate the conjugate transpose. This is essentially just the pi j I of the x and dx. And this, by definition, this is essentially just the same as what we did define as a c pi of ji, but you scale it by 1 over d pi. All right, so what we have is that now if you consider your f of x, I want to get rid of the ij, so let's try to rewrite in the following way. So I have that this is the summation over all the equivalence class of the irreducible representations pi, and then I sum ij from 1 to d pi, and then I have a coefficient Cij, c pi ij of the pi ij, all right? And so now each of these Cij, I can write it as some kind of the ij entry of the Fourier coefficient. So this is, I write it the sum over the same pi, and then ij, and then the Cij now becomes d pi times the f hat of pi of the jith entry of this, and then I have the pi ij. Okay, I should say x is in here. Okay, x is in here. All right, so this is just the f hat of the jith entry multiplied by the pi of the ijth entry. So now it all comes back to a little bit linear algebra. So if you have a, b, there is a n by n matrix, and if you want to sum up all the ij and then you have the AJI times B of IJ. So you can think about this really as the trace of A times B. Okay, so you multiply A and B, and you do the first row multiplied by the first column, and you end up with these I. Basically, the j is going to be equals to 1, and you sum out over all the I going from 1 to n, and you do the second row versus the second column, that's j equals to 2, and so on. So this can be written as a trace. Okay, so each of these summation, these double summations now becomes a trace. So now I have the summation over all the pi, and then I just rewrite as d pi times the trace of this n by n matrix, basically the Fourier transform of my f hat, multiplied by the pi x, another d pi by d pi matrix, and you take the trace. And the nice thing about this trace is that it doesn't depend on the choice of the orthonormal basis anymore. Okay, so the trace is really preserved under any orthonormal basis. So that's a much better formula. I don't need to worry about the choice of these orthonormal bases for each of these h pi. So as a quick corollary, so this is looks like the Parseval's equality. So if I have f inside the L2 of G, then I have the norm, the 2 norm of this f is essentially just summation over all the equivalence class of irreducible representations of this d pi times the trace of the f hat of pi. You do the complex conjugate and multiply by the f hat of pi. Okay, so you do that. And there's another way of thinking about this, is that if you recall from linear algebra again, you can put some norm on the n by n matrix. There are many ways of putting a norm. The one way is called the Hilbert-Schmidt norm. So this is not related to the integral operator, but this is just the summation. So let's say squared is the summation of the aij squared. Okay, so you treat a as if it's in the R or the n squared dimensional matrix. So you treat it as a vector. Okay, so the norm as in the L2 of that space. So this is called the Hilbert-Schmidt norm. So the Hilbert-Schmidt norm is actually just equals to the trace of the A star A. Okay, so there in fact are the same. So what you do is that, well, now each of these elements, you can understand it as the Hilbert-Schmidt norm of this n by n matrix. Okay, so each f hat of pi is an n by n matrix. So this is also understood as you sum over all the irreducible equivalence class, and you do the Hilbert-Schmidt norm of the f hat. Okay, so f hat squared. Okay. So let's prove this. This is really simple. So we have the F2 norm from what we had before. This is going to be equals to the summation of for each pi, and then you do the summation of the Cij, the whole thing squared, and then you multiply by some scalar. So you have the 1 over d pi, okay, as your scalar. And then here ij going from 1 to n. And each of these Cij, you can really just, well, when you scale it down by the d pi, that's just going to be the ijth entry of your f hat, okay? So this double summation is essentially just the summation of the f hat of pi, the ijth entry, the whole thing squared, okay? So you do that. And this, by definition, is just the Hilbert-Schmidt norm of the, the Hilbert-Schmidt norm of your matrix f hat of pi. Okay, so this is hs squared, and that's also given by the trace formula. Okay, so they're really the same. Okay, so let's finish another nice way of computing the 2 norm. And I just want to briefly mention that this f to the f hat really looks like a Fourier transform we saw in the abelian case. So I just want to observe the following. So this map f from the f hat really satisfy many nice things. So First of all, is going to be linear. And second of all is actually respect the convolution structure. So if you have two things, if you convolute, you have it's essentially just the g hat times the f hat, okay, the dot product. And then if you do the involution and then you do the convolution again, that's if you evaluate pi, that's essentially just you do the conjugate, okay, the complex conjugate. All right, and finally, if you do some left and right translation of it, okay, the Lx hat of a pi, what you can do is that you do the Fourier transform, but then you right translate it by the pi of x inverse. And if you do the right translation, evaluate pi, this is just left translation by your f hat of pi. All of these you should compare it with the Abelian case, okay, compare with the Abelian case. And you really see that these Fourier transform, they really look like each other. The only difference now is this f hat is going to, well, it's not going to be a complex value thing, okay? So it will take a finite dimensional irreducible representation and returns a matrix, and the size of this matrix really depends on the dimension of the representation. Okay, so they're not exactly the same thing, but as you can see, at least the L2 theory have some similarity to the Abelian case.